Oh, yeah.
Good evening. This is the final time that we are gathered together. Anthony is so happy to be done with me in this role.
I'll bug you next semester.
Yeah, I'm sure that I'll be seeing a lot of you after this semester. But with our final day in class,
Excellent.
no, with like leadership roles.
No, it meant you're going to teacher.
Or playing soccer together, if anyone wants to play soccer after this. I love playing soccer with people who are not in my class, because if they're in my class, then there's jokes that happen that probably shouldn't. So, let's start out on a more focused note. As class goes on, I will come around and hand back a number of things for you. Everything, I think. Yeah, I feel like the word of the last few days, like the amount of grading I've been doing.
You've done a great job.
Alright, so to start with, since I've been grading a lot, including your exam wrappers, do this for me please. Draw these two things. And take about 1 minute to do that. Please draw these and accurately include everything that you need for an accurate drawing. There's no sheet to start on. We will be working first on the in-class worksheet yesterday from Monday. No, in-class worksheet from Monday. All right, a couple more seconds to finish drawing those two structures. Two structures. We're drawing these two structures. All right, a couple more seconds. All right, let's start with the process. I know this is a Gen Chem 1 topic, and I'm glad I didn't teach any of you Gen Chem 1, because what I saw in those exam wrappers really was kind of painful. And what I see walking around is pretty painful. So, how do we draw a Lewis structure? So the first thing we need to do is, okay, before we even count valence electrons, we need to know what the formula is. So for this particular compound, what is the formula, Echo? Great. For chlorate, the reason we need to know that one is because for chloric acid, when it has an H+, it's a strong acid. Okay? And then we say, how many valence electrons are there? So many people skip that now. And I know that it was like first semester, but if you're going to do any chemistry from now on out, you absolutely need to figure out how many electrons there are, and then after that, where to place them. Okay, so how many total electrons do we have? 24 plus 7, 31. So we have 32 electrons, and then one of those atoms is going to be central. So what I saw a lot of people do was this, and then either not count electrons or they did this. This looks great, right? Are there any formal charges? Lots. Okay, so each one of those oxygens has a formal charge of -1, -1, -1, -1. Does that sit well? Just starting out, does that sit well with you guys? No. Okay. What's the formal charge in the chlorine? It only gets to count 1 from each of these bonds. It should have 7. So that has a formal charge of +3. All right. Terrible. Almost everyone that I saw their exam drew a variant of this for perchlorate. Even if you got to the point of saying there are, so this was a question about polarity, right? Molecular polarity. So yes, you would end up kind of with the right answer because you would determine the steric number from this. The steric number is 4, which means it's tetrahedral electron pair geometry. All the dipoles in this molecule will cancel each other out. But this is the wrong Lewis structure. So what do we need to do to minimize those formal charges? Let's make some double bonds. Can we do that? It's chlorine. Can we have more than 4 bonds to chlorine? Yes. It's in period 3 or below, so there's empty d orbitals those electrons will spill into. So the way we do that is let's go ahead and draw lots of double bonds. Josh.
Is this resin structure as well?
Does this molecule have any resin structures? We'll get to that in 1 second. Are you guys okay with what we drew? Any formal charge on chlorine now? 1, 2, 3, 4, 5, 6, 7 electrons. It should have 7. The only one that has a negative charge now is this oxygen at the bottom. That is an appropriate Lewis structure. If you do not know or remember how to do this, there's like 6 POGL activities. POGL, what is it, like 12 or 13 is where it starts, and it goes all the way to POGL 18 or something. Go back and do those. I guarantee you that you will have severe issues on the ACS final if you don't know how to draw a Lewis structure. And heaven forbid you go to organic chemistry, you're done on day 1 if you can't draw Lewis structures. Like, it's all about knowing how to draw Lewis structures. Is that a fair statement, Janesh?
That's the first chapter.
Yeah. And they fly through that in like a day or 2. So you need to be able to draw Lewis structures. All right, so Josh, are there any resin structures?
I think so.
How many?
Could be 3 others just like that.
3 others?
Well,
In addition to it.
Yeah.
Yeah.
Just like
So the negative charge can be here, 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 or here. All right. 4 resonance structures. Which one of them is found most often? Which one, love? None of them. Why? It's an average of all of them. Okay? So that is why this molecule is not polar. So there are 4 polar bonds. They're all equal in length, in number of electrons, and density of electrons, and all of that, because it's an average of all 4 of the resonance structures. This is a limited model. It can only tell us so much. So we have to look beyond this drawing and say, well, I know that this isn't actually how it looks, because this bond is a single bond, looks longer than the other ones that are double bonds, but it's not. If we were to go and take an X-ray picture of it, we would see that all 4 of those oxygens are equally spaced around that chlorine atom. Avery?
For the oxygen on the left, shouldn't it
Oops.
only have...
Try to erase all the stuff that I had drawn and make it more accurate. I got almost there. All right, I saw a lot of people throwing too many electrons or not enough electrons, not doing formal charge, not thinking about you can exceed the octet rule with certain atoms once they're below a certain group. All those things seem to be lost when you guys were working on this. So it really concerns me. Second molecule, ozone. Question?
Okay, I just want to make sure. I'm sorry.
Thank you. So I'm drawing this quickly. One of them, we left all 3 pairs of lone pairs. All right, ozone. What's the formula for that? You guys remember? O3. Go ahead and draw the Lewis structure. Do you remember how to do that?
It's not like in a certain part of the atmosphere. It is the atmosphere.
It is, yeah. All right, let's discuss. Last day you ever have to do this.
Until it catches on for the rest of the chemistry.
Unless you guys make the rest of the chemistry department do it. All right, how does this look?
Looks nice.
The middle oxygen has a +2 charge.
So what did I forget to do starting this entire thing? Count valence electrons. I didn't even include enough valence electrons on this, right? So I should have a total of how many valence electrons? And in this molecule I had 2, 4, 6, 8, 10, 12, 14, 16. So then that's an easy fix, right? Done. Why not?
Because it exceeds the oxygen.
Clear? I can't expand the octet of oxygen because I heard some people say it's in period 2. Okay, so not okay to do. So what do? Let's remove one of those bonds. Now it's okay, right? We have 8 electrons around that central oxygen. 1, 2, 3, 4, 5, 6, 7, 8. But I removed electrons, so I got to put it somewhere else, right? Let's go ahead and put them on that right oxygen. Where else am I going to put them? Let's look at formal charges now. Far left oxygen, formal charge.
0.
Middle one only gets to count 5, right? Lone pair, 3 from bonds, that counts 5. It has a +1, and the far left has a -1. Overall, the formal charges have to add up to whatever the charge is on that molecule. This is actually the most accurate structure of ozone. Josh, your question.
No question.
What's Josh's question?
Oh, resonance structure.
Are there any resonance structures? Well, I'm glad you asked, Josh. Yes, there are, in fact. Where would the resonance structure be for this molecule? Okay, so one of these lone pairs would move into a bonding position, but then the octet rule is exceeded, so that means that one of these bonding has to become a lone pair on the other side. Right, so everything shifts to the other side. Which one of those is most accurate? Neither one, right? Is this a polar molecule? Why? It's bent. Steric number 3, it's bent. It's polar, right? Say again. Kayla, next slide.
It's something with itself.
So what does that mean? Okay, if you don't have polar bonds, who cares about the molecular shape, right? There is no, where is the center of the partial positives and the center of the partial negatives? Remember that activity I just gave you back? And that series, that was homework 1, by the way. You're welcome for finally getting that. I keep up with a lot of stuff just this semester. It's been kind of bad. All right, so first, are there any polar bonds? If the answer is no, then you don't need to do anything else. But if there are polar bonds, like for perchlorate, you guys have to think about the molecular shape. And so that was really concerning when we went back and looked at, in addition to drawing the Lewis structures, determining whether a molecule is polar or not was something that you guys really struggled on. Even if you got it wrong in the exam, trying to do the exam wrapper, you showed, a lot of the class showed that they were struggling still with that. The example was this molecule. Is this polar or not? Yes or no? Talk to your neighbor. Think through those 2 steps I just discussed. Raise your hand if you think that this molecule is polar. Yes. Raise your hand if you think this molecule is not polar. All right, which is it? Argue. Who wants to argue their case? Logan, what are your thoughts?
Nice.
Why?
Come back.
Okay, so the two questions we have to ask first are there any polar bonds? If there's no polar bonds, we stop, right? Don't waste any more time. Are there any polar bonds? Yes, there's two. Second question is shape. Is the shape linear? No. How do we know that? How many, what's the steric number? We have 4 groups around this. That means it's tetrahedral. This is shown as a line. It's not. This is a single bond. It's free rotating. So that means that these 3 groups are kind of in a pyramid shape. These 3 as well. And they're constantly rotating. And so it depends on if they line up perfectly on opposite sides. There's a distinct second when they're not polar, when they cancel each other out. But majority of the time, that's not true. So this is absolutely polar, even though it has polar bonds, even though the lines look like they're pulling in different directions. This is a 2-dimensional image. We need to think in 3D. I spent probably way too much time going through your exam wrapper and giving a ton of feedback. Please use that. The final exam will cover all topics from that, as well as the things on exam 3 and 2. So I implore you to go back, look at what you were able to get credit back for, what you weren't. Not right now, please. We have a lot to focus on. But my main takeaways were concerned in these major areas. And if you are still struggling with those things, I have office hours, Friday, or exam review sessions, let's call them that, because that's what they're going to be, right? Friday, 1 to 2:30, Monday, 4 to 5:30, before our exam. Tuesday, I'm going to add hours, and actually I'm going to ask some questions about that right now. So I want to know, Peter, where's Peter? Were you able to bring just 2 packets? Was everyone able to grab the packets that arrived towards the beginning of class? If not, maybe you can raise your hand and Peter can drop them by. Anyone still need the packets? One of them is I decided to give you guys my final exam from one of my previous classes. What that means is you have a lot of practice problems and a lot of topics. So supplemental instruction this week will be optional, aka not for credit. So you can choose to go or not if you want. It's a great opportunity to study with your peers and to do it in an environment with someone who can really help guide you. So Josh is going to be running these. Vocal activity 56 is, I was looking over this afternoon, it is a lot of reviewing of what we're going to be talking about in class today. So that is also another review tool for you. We will not be doing activity 56 in class. It will not be due for credit, but it will be a fantastic way to connect everything together and practice what we're doing in class today. So what I want to know is, since this is not for credit, this is only to support you in your learning, I'm going to offer these 3 times, and I want to know if you will go to these so we know which ones to offer. Josh is going to offer most likely 1 or 2 of these times. If people aren't going to go to them, we're not going to hold them. We're going to have a 5-person minimum for them. So for this time tomorrow, 4:30 to 6 p.m. in ETAS 406, can you just respond and clicker, yes, I'm going to go, or no, I'm not? The other 2 times for reference are Saturday 12 to 1:30 online, and Tuesday 10 to 11:30 in person. All right, so for the Thursday, have you clicked in whether you're able to go or not, or would go to that? I'll show the other 2 in 1 second. So I just need to know if people will go to this one. Okay, so we have 13 people that said that they'll go to this session. Okay, so it looks like tomorrow is a go. The second session is Saturday online. We have 5 or more people that will go to that session. You don't have to go to all of them. You can go to none of them if you want, Shanaja. So the one on Saturday, so the most likely answer is no. because it's really hard when it's a small group like that to record. I will post the answer key to the exam, so you can go back and kind of work through problems if you want to use that as a tool. But I don't know that I'm going to be able to record it in a way that's helpful. So we have 10 respondents saying that they would go to the Saturday one. We're either going to do that or Tuesday, so let's see which one we have more of. So we had 11 people say they would go to the Saturday. How many people would go to Tuesday, 10 to 11:30?
That's your office hour.
No, this is also Josh. Josh is either doing one of these two in addition to this one. So there were 11 people that said that they would do this. If there's more people that say they'll go Tuesday, Josh will hold that one instead. Christina? Yeah, not mine. Okay. So we have 17 people that said that they would go to Tuesday. So the two ones that we're going to, Josh is going to hold for you guys, are these two. Okay? Don't forget, my office hours or exam review sessions are also going to be on Friday 1 to 2:30, Monday 4 to 5:30. Or should we do that earlier in the day? Because it's the exam day.
Does that mean we can be there?
Well, no, because I have an exam at 3.
Raise your hand if you would go to office hours earlier on Monday, maybe closer to noon. Okay, so let's do.
So, is that exam Monday, is that like exam 3? So
Correct.
big one
Exam 3 on Monday is only for things from exam 2 until the end of the semester. The exam on Wednesday night is the entire semester.
But that's
ACS is on Wednesday. They're equally weighted. All 4 of the exams are equally weighted.
so you're not having, you're like you did last semester.
And then on Tuesday, no, I do not have 2 exams. There will not be 2 exams this semester. So Tuesday, Josh is going to do 10 to 11:30. I will hold a session in the afternoon. And I'm trying to see on my schedule if I have anything next Tuesday. I do not have anything on Tuesday. So if Josh does 10 to 11:30, I'll do, 2 to 3:30? Raise your hand if you would go to 2 to 3:30, if that would work for you on Tuesday.
Oh, yeah.
There's no classes on Tuesday, there's no exams, it's a study day.
Can we go from 10 to 2:30? I'm not being serious here. I'm away on that. Tuesday, there's no class. Just concentration. Not again, bro. You got class on Tuesday. You're wrong.
So you're not doing it. What is it tomorrow?
Correct. All right, so let's clarify. Josh is doing the 2 times that are circled. We'll send out an announcement with the location of these. I am doing exam review sessions Friday, Monday midday, and Tuesday in the afternoon. Okay? If you cannot make any of those, come up on the board after class, write your name down, and I will survey those people and find a time that works.
So you're saying there's 5 reviews?
There are 5 review sessions between now and next Wednesday. 2 of those are on Tuesday. So exam 3 is on Monday night. So these 2 don't help for exam 3. All right. Any other questions?
3, the other ones are from final, basically.
Correct. So my final exam, which is, if you haven't grabbed it, it's in the back. That is a study tool for the final. There are parts of it that are for the end of the semester, so you might want to focus on that for exam 3. And activity 56 is also going to be really good study material for both exam 3 and the final. All right, any other questions? All right. Last logistics. Exam. All these scores are updated on Blackboard. The only one that's not is I still need to post your homework for this week so you can practice what we're doing Monday and today. And then there's going to be a post quiz on that. So should there be a post quiz?
No.
Okay. Fair. I mean, the post quiz is your exam 3. Let's be honest. Okay. Good to go? You guys are going to miss this class. You know it. Sorry, I can't hear Shanidra. Can you guys help out?
And then you said the last 2 assignments that you posted up there, the practice questions are not for grade.
Yeah, they're listed as for credit only, so it shows up in your list. They're worth 0.1 points, and a normal homework is 10 points. So it's not really for credit. It's to give you opportunities to practice. Last question.
On the ACS final, is it going to be broken up into like groups like this?
No. The ACS final has 70 questions, multiple choice, over the entire Gen Chem 2.
What thing is going to be
Really quick question?
I was just going to ask, are we doing like the little 10 question thing on this exam right now?
Oh, there will be an exam scratch off on Monday night. Yes. So, and I will, one more thing. For exam 3, I will post the answer key as soon as we leave this room. So if people wanted their exams back immediately, I can't do that. I can't grade that fast, right? Peter and I are not that amazing. But the way that as soon as you leave here, you can go back, look at the answer key, figure out, I really didn't get this concept as well as I thought. And that way it'll help you study for the final on Wednesday. Kind of a compromise. Nope. The one I gave you is a previous exam. It gets you to practice some problems. It gets you to see how I ask questions. But that was a totally different class of students, a totally different cohort. It was students who were taking integrated biology, chemistry, and so there were more biology-oriented questions. So take it for what it is, a previous exam. All right?
Does this mirror our exam 3? Or, like, are the concepts similar to our exam 3?
No.
Okay. So this
That
would
is
be,
a
like,
final exam for an integrated biochem course. All right? So that means that it is not an exam 3, that is an exam 4. Since I'm not giving you my exam 4, I gave you an old one so that you can see what that is. So part of that exam would be like exam 3. Does that make sense? The last part of it. All right, so our goal with the next 45 minutes is we have to be super focused and on task. Can you guys help do that? If we don't do that, then you guys are going to be left without all the things you need to perform well in the final exam. All right? So let's do this. This is the biggest component here. Is looking at how these 3 things relate. E cell, K, and Gibbs free energy. So I want you to be able to draw a Gibbs free energy diagram based off of any of those 3. And then we're going to be talking about spontaneity of a reaction. What makes a reaction spontaneous and not? And Angel, these are on the worksheet for today if you don't want to write them down. And then what about a reaction at standard conditions, not at standard conditions? So basically what I want you to be able to do is convert between these 3 things. Any one of these 3, you can calculate the other 2. All right. So let's do this. If we're at standard conditions, what is Q? What?
Enjoying the Kool-Aid jammers? You're doing the Kool-Aid jammers.
More sugar.
Okay, now
They're like organic.
All right, a couple more seconds. Closing out. Are we really missing 10 people? 12 people today?
Lab final recite. That's it.
All right. So the majority of people answered based on this idea, but remember, anytime we're talking about Q and K, regardless of what the K is or what the Q is related to, always go back to concentration of products over concentration of reactants raised to stoichiometric coefficients. What are the concentrations of everything when we're at standard conditions? 1 molar. So Q is always 1 at standard conditions. All right, so let's go back. This equation that we talked about last class, that the Gibbs free energy can be calculated based off of the relationship between where Q is compared to where K is. Remember the other way that we could write this equation is up in the top right corner here. That rule of logs allows us to say RTLN Q, that divided by means we can subtract RTLN of K from RTLN Q. Same exact equation. So, if we're talking about standard conditions, if we were to say standard conditions here, what would change about that equation? What could we simplify about that equation?
It would just be negative RTLN K.
Q is 1, right? So ln of 1 is 0. So that means that Gibbs free energy at standard conditions minus RT ln of K. So if you're given Gibbs free energy at standard conditions, it's been simplified because of this relationship. That means that automatically we can calculate RK. Equilibrium constant. And that'll tell us whether it's product favored, reactant favored. So let's think about what that means then. If we have a delta G naught at standard conditions, remember, that is positive, what can we say about the reaction? Which one of these makes sense? This is from the worksheet from last class. This is written on there. Let's do another 10 seconds. All right, can I have a volunteer? Which one of these do you think makes the most sense and why? How did you get there? Logan, what did you say?
So I said that the answer was C, that the reaction loss is left, because during last class we discussed that when delta G naught
Avery?
is negative,
Hannah?
then the reaction is then favored, so it would be product favored. And since it's positive, it would be quite the opposite. So if 1 is where we need to be, we're going to go to the left of that. If the right is
So, this is exactly what I want you guys thinking when you have a positive Gibbs free energy at standard conditions. Why? Where is Q in this reaction? Where would I draw Q? Tripty? So Q is right there. So that means that in this standard state right here, if we were to let this reaction go to the most stable mixture, it is going to favor a higher proportion of reactants than products. Positive means it's going to be spontaneous in the reverse direction. So we need to look at that sign of Gibbs free energy at standard conditions, and it tells us which way this graph lies. So go ahead and on that, go ahead and draw the opposite on the other diagram. So the worksheet from last class, can I hold it for 1 second? On the back side of last class's worksheet, you had 2 blanks. Go ahead and draw one for Gibbs free energy as positive and one where it's negative. Check with your neighbor and make sure you can define Y. Show where Q is at standard conditions. All right. So what do we draw for our other graph? Can I hear from Austin? What did you draw for if you have a delta G naught that is less than 0? So what would you draw? Nabil, do you mind closing that? Thanks. So where would the minimum lie? What do you guys think?
Yes.
Absolutely. So the sign of Gibbs free energy at standard condition basically helps us draw this. What about the magnitude of it? What about how big, right? So it could be 0.1 or it could be 10,000. What does that magnitude tell us?
How more would be favored? Or
How much it's favored? So how far that minimum is away from the center. If Gibbs free energy at standard conditions is 0, it's nowhere away from the middle. It's at the middle. But the bigger, the more positive the number is, the further left that minimum is. The more negative it is, the further right that minimum is. Because remember, that relationship up there in the middle says that the bigger the magnitude of Gibbs free energy at standard conditions, the bigger these two things, if we're talking about the same temperature, right? Those two things are not influencing it nearly as much as your equilibrium constant. And it's an exponential relationship. So, what I want us to be thinking about for the last part of class is how we can harness that energy in order to do work. So, here's one way to look at it. An endergonic reaction, one that is spontaneous in the reverse direction. How do we get that reaction to progress against Gibbs free energy? How do we force this reaction that is not spontaneous? We want it to go this way. How do we force an object to move against how it's supposed to go, Danielle?
Could you change the temperature?
So temperature might have an influence, for sure. What if we tethered it to a reaction that was favored? So if we have another reaction that is favored to go in the forward direction, greatly favored, then we can use that energy that is dissipated from that in order to drive other reactions. So that's how all biological processes and chemical processes work. Is that most reactions that are unfavored can be pushed to be favored by having them driven by something else. So let's skip this. And we're going to bring a couple of different pieces together now. So I want you guys, I believe that this is the first thing on today's worksheet, in-class worksheet. So there should be a 5-1 worksheet that you guys have. Question number 1. What is equilibrium constant? The conversion of ATP to ADP given Gibbs free energy at standard conditions. Yeah, the answer goes, okay, I'll give you guys about 1 more minute.
Oh, you did. Ah, I see what you there. He's sneaking around. I know. I almost so Oh wait,
Judging by the number of responses, I'm guessing you guys are not so comfortable with this.
Nope. I didn't put my name yet.
What's going on? All right, so this is kind of going back to really, really basics. What do we know? What are we trying to find? How do we solve for it? So what do we know? Chelsea, you want to start us out?
We know the Gibbs free energy and the reaction.
Great, at standard conditions.
Yeah.
What else do we know?
We know the equation,
What equation are we using?
negative RT, ln K.
Great. And we know R. Do we know the temperature?
Yeah.
So we know everything. The only thing we don't know is what we're trying to find, right? So did we get lost up to there or after that? The mathematical calculations?
It is.
Okay. So if you guys are still struggling with logarithms, I can guarantee you that about, let's say 20 to 30% of the ACS final exam requires you to manipulate logs. That means that your grade will change by 1 to 2 letter grades on the final exam if you don't go back and learn how to manipulate logs. I've tried to tell you guys all semester, we try to have that log quiz. Please figure it out by the final exam. I don't have any influence on it. You guys are going to be held to that standard. So if you're uncomfortable with this, make a note, a big star. I need to go back and learn how to rearrange these equations. All right. So if we go ahead and plug everything in, by the way, on the final, on my exam 3, I will give you a number of different versions of R. Make sure that you check units and make sure your units match with what you need. So if we rearrange the equation, hopefully you guys were comfortable doing this, at least isolating ln of k. Right? And then we can find ln of k, we can put all of our numbers in. How did I get this?
You put times 10 to the 3.
Kilo times 10 to the third. Everyone catch that? Almost everything for Gibbs free energy is written as kilojoules. 298 Kelvin, all of our values, our units are going to cancel out with joules and joules. Kelvin and Kelvin is on the bottom, so we're going to end up with moles on the top. Does that make sense? Joules per mole, Kelvin. I missed some units, didn't I? Okay? So then how do I find K? What do I do? Anti-log, natural log is e to the. So e to the 12.316. Does that make sense? What do we think about that number? What do we have guessed that would be what we're expecting? Why, Austin? Negative Gibbs free energy, what does that tell us? Okay, so it's really important to state negative Gibbs free energy at standard condition. So that means that if we have our Gibbs free energy diagram, this is going to lie to the right, which means it is highly product favored. Would you say that this is highly product favored? Okay, so you can kind of keep that ballpark in your head. Negative 30 kilojoules gets you a really big K value. So if we had a delta G naught of 1, we would expect a number much closer to the middle, much closer to K of 1. Kayla?
So it's whenever delta G is less than 0, K should be greater than 1?
Correct. All right. So I just did this. Forgot that I was going to ask you guys to do this. Could you do this? If I gave you delta G naught, could you draw the Gibbs free energy diagram? If the answer is no right now, then that's something I want you to practice. So, if this is our Gibbs free energy diagram, and we drew it from the information at the top, where's our Q value? What Q are we using to draw that diagram? Standard conditions, right? Q value of 1. We know that from standard conditions, the reaction favors products. That's what that negative sign on delta G naught means. That's why we are able to draw the minimum to the right. All right, so let's think about the next question then. If instead of standard conditions, if we had a 10-to-1 ratio of reactants to products, where would Q be? And then think about how your Gibbs free energy would change. What about it would change? What about it would stay the same? Go ahead and talk to your neighbor. Click in your answer when you're ready. Future break. Corbin, what did you guys discuss? Where would Q be on this graph?
We said since the ratio is 10 to 1, and there's a lot of reactants and very low products, we said that it would start left to the middle, A.
And most of the class agrees with you. I do as well. So our Q value would be pretty far to the left. So then what does that mean about the sign of Gibbs free energy? Why did I get rid of the little circle here when I'm asking about Gibbs free energy now? We're not at 1 molar of everything, right? We changed. So I want to know, what is the sign of Gibbs free energy? Is it the same as we have for standard conditions? Is it different? Or did we go to Gibbs free energy equals 0? Go ahead and talk to your neighbor and click in your thoughts. Do a couple more seconds. All right, so I want you to reevaluate. Know that we are not on consensus. Which one of these would make more sense? Is the sign of delta G at this Q going to be the same, which is negative, or is it going to be positive? You were split between those two answers. So talk to your neighbor. Try to figure this out. Ask one of the supplemental instructors as well. We'll help you out. That Q. So if we're at that Q value, we're crossing the red line. What's going to have to happen? Say again. Unless you guys discuss that. All right, click in your final response. So very interestingly, I think this might be the first time I've had this, where I didn't say anything. Granted, you do have little helper bees all around, but the class shifted drastically in one direction. Hopefully it's the right direction. Kalia, who did you convince?
My friends here on the third row.
In the third row?
Yes.
Which ones?
We all had the same.
So who are you talking about? Tripty, Savannah, and Logan?
Tripty said that it was B, but she was thinking it was magnitude.
Same thing.
Okay, so Savannah, can I have you describe your group's discussion?
Come on, Savannah, you got it.
Okay, that discussion was really
Okay, Tripty, can you describe?
At first, I thought that since Q is more further to the left,
Mohib, Mohammed, please. Go ahead.
more further to the left, the number would change, but the sign won't change.
What do you guys think about that? What does a negative Gibbs free energy mean?
To the right of Q.
It means the reaction is favored in the forward direction from where we are. The ones with standard conditions just happen to be where we're in the middle, and then the question is, does the reaction lie to the right or left from there? This is just not in the middle, but we're still asking the same question. To get to the equilibrium, is the reaction going to proceed left or right? The minimum of the energy diagram is down there at the bottom, right? That's the ideal mixture of reactants and products. We're way away from that. So in order for this reaction to reach equilibrium, then we're going to have a release of Gibbs free energy, a negative sign, meaning it goes to the right. So then what is different about this? The magnitude. All right, so if we look at, I can't remember if I actually had that as a question or not. Is it a question on the sheet?
Oh, it's right.
So our Gibbs free energy here, the amount of energy released to get to equilibrium is very small. But if we're starting way further up the hill, we have a lot more potential energy, chemical energy actually. But that's the relatable thing, is talking about potential energy. That this is going to be able to release a lot more energy when it, on the path to equilibrium than this one does, even though the sign of Gibbs free energy is the same. So the magnitude of delta G is going to be way greater than the magnitude of delta G naught. Logan?
But another way of looking at it would be that we're still losing energy from where we started from?
So the reaction is releasing energy to the surroundings, yes.
Well, I was saying like related because delta G is negative, therefore that means like you're losing. When it's positive, it's gaining toward delta G.
So the sign, I want to be careful that the sign, so both, if we were over here, you could say the same thing, right? So I don't want to use the sign to describe going from up to down. I want to use a sign to describe going left to right. So the reaction here is both going down, which means it's not at zero, and it is going to the right, which means it is a negative sign. If we were on the far, if Q was on the far right side here, then we'd end up with a still going down, not at equilibrium, but the sign is positive because we're converting products to reactants. Okay? Questions? You guys feel like you do some pretty good calculations with this? All right, so let's go ahead and talk about this at standard conditions. If we couple these two reactions together, how much energy is left at standard conditions?
You told the wrong, so I was like, oh, like that's smart.
Out of anyone he'd want to spend his birthday with, it's us.
But, I mean, is that what, I mean, do you have leftovers?
They're coupled. They're two coupled reactions. They're separate, but one drives the other. Question. All right, so what we're talking about here is that these two reactions are coupled together. That this reaction at standard conditions, is this favorable or not favorable? Glucose going to glucose 6-phosphate. Not favorable in the product's direction. Is ATP to ADP favorable? It is favorable in the product's direction. So if we want to make glucose 6-phosphate, we can use the top reaction to drive the bottom one forward. So we can look at the overall reaction as the sum of the two reactions. It should look familiar from when you did enthalpy calculations in first semester, Hess's law. When you did entropy and enthalpy calculations this semester. So hopefully this trend looks the same. And so if we couple these two together at standard conditions, we're actually left with an excess of 15.4 kilojoules per mole. What does that mean? Say again?
The overall reaction is favorable?
The overall reaction is definitely favorable. And in fact, we could almost run this reaction twice if we had enough ATP and water and glucose, right? So, one of the things that you guys missed, by the way, on that last problem, units. We got one, and a lot of people do it, negative 15.4. It was alphanumeric on purpose. I want you guys thinking about units. All right, what if one of these wasn't kilo? But then if you just put in a number, you don't think about the units, it's really important. So be really careful. Please include the units.
It would be a dirty question.
All right, really quick question. We have 15 minutes left, and we're going to get through some of this. We're going to crush this. Which of these reactions would require the input of ATP at standard conditions to proceed? Go ahead and type in all the numbers, right? So if it's 125, type in 125 cent. And for the person who already submitted, please resubmit.
Is there a comma?
I believe you have all these on your paper as well.
What does it matter how close a shake of the head, very helpful.
All right, closing up. So our most popular answer is all of them? Okay, let's revisit that. Was it not all of them?
Your brain working too fast. He just like,
1, 2, 3, 4.
7, 8, and 8.
So 5 and 6 are the only two.
And
9.
And 9. Okay? I agree.
It's all.
Which of these can we use to produce ATP? They did all the positive ones. Alright, so go ahead and answer this question. Which of these could we use to generate, and you can put 0 if you think none of them. That is a legit answer.
No. Could be.
You feel like this is a setup?
Couple more seconds. Closing out. All right, a very large majority of people said all 3 of the ones that are spontaneous at standard conditions could actually drive the generation of ATP. Why? How did that make any sense? What are we talking about?
The magnet.
Madison, you want to share your thoughts?
Well, I had a question as well. If it, I did put 5, 6, and 9 because it was the number was greater than the Gibbs free energy of ATP. So if it was smaller, would that still be the same answer?
So there's one big piece that's an assumption I think that's being made that we need to get out in the open.
Positive or negative?
Is this what we're comparing it to, or what's different about it? Matt, what are your thoughts?
If turning ATP into ADP, releasing 1-phosphate releases 30.5 kilojoules, and putting that phosphate back onto it should require 30.5. So any
Pause.
negative number.
Great. So let's just hang on that, and then we'll have you finish in a second. Is that the logic you guys used to get there? So in order to do the exact opposite of this reaction, the sign of that Gibbs free energy reaction is the opposite. So the question is, what of these can drive plus 30.5 to completion? That's what Matt was talking about. And then finish, Matt? So once we think about the plus 30.5, what can drive that, then what did you say?
Anything of a greater magnitude that's negatives has more energy, can release more energy than is required to make ATP.
So we can have any of these 3 release enough energy to drive a plus 30.5 kilojoules per mole reaction. Clear?
I was literally just thinking about the question before this, where we subtracted it, and that's how I got my understanding. Is that not going to get me far?
So remember that everything we're talking about is really based on the directionality of the reaction.
Right.
So if you do a reaction in the opposite direction that has a positive delta G naught, it means you're going to have a negative, it is spontaneous in the forward direction then. So pairing them up in a certain way is really important to think about how those come together. So, last one. What about the production of NADH and protons? Which one of these can drive that reaction? 15 seconds. Couple more seconds.
Let's do like a minute.
All right, closing out. So the majority answer was 0. Why? Sam, nice and loud.
None of them have enough energy to do the reaction.
This reaction requires too large of an input of energy compared to that any of these are able to offer. So does that mean that our bodies don't produce NADH plus H plus from any of these? Do you guys recognize these reactions? Please tell me you recognize what they're related to. Glycolysis. All right. So these are all the glycolysis reactions, and we know that it does generate NADH and H plus. So what's going on? What are we missing? What are we missing? This does happen. It does happen from some of these steps here.
Catalyst.
Nope.
Wait, did you just ask if we use more than one reaction to pull it or something?
Correct. He asked if we could use more than one reaction to pull it. The answer is no. So, what do you guys think about the answer to this question? Are cellular conditions standard conditions? I'm not going to do clicker. What do you think? Yes or no? No! Remember we just did a problem where we said we're standard conditions. Well, we can move it further and increase the magnitude of delta G by changing Q away from 1. All right. So in glycolysis, there are a number of steps that do generate NADH and H plus and generate ATP. And we have to think about what the concentrations are, and the concentrations will actually influence that. And if you look at the big kind of zoom out, like cartoony version the biology classes show, that you end up with huge drops that release NADH, right? And so that's energy being stored that can be used then to drive other reactions in the future. So let's take a look real quick. We already walked through this before, right? So we said that Gibbs free energy at standard conditions is simplified to minus RTL and a K. So then what does this equation become if we substitute this for this guy? Have you guys used that version of the equation yet? Do you guys see that Gibbs free energy at standard conditions is half of this equation? So then what is a simplified version of this equation? So that means if I were to go to a table, I could find what it is at standard conditions, and then if I know what my Q is, I can say, well, it's not actually this because we're not at standard conditions, but I know Q, so from that I can calculate what the actual Gibbs free energy is. There's multiple ways to think about Gibbs free energy. It's related to entropy and enthalpy. True. It's related to equilibrium constant and concentrations. True. It's related to E cell. All of those are related together. They're not in the same equation necessarily. So, let's add a couple more in there since we're talking about it anyway. Have you guys been using this equation? In your POGL activities? Gibbs free energy at standard conditions is equal to NF E cell at standard conditions. E cell, you guys know how to calculate this? This is for galvanic cells and those kinds of things, right? What is N? Number of electrons. F? Faraday's constant. You guys are doing calculations with this weekend, right? Okay, I'll add some this weekend. You'll get to practice. This is how I love to end the semester. Everyone fully understanding everything. We're good. All right. So let's real quick look at what that means. If we have a spontaneous reaction, what is the sign of Gibbs free energy? Negative in the forward direction. What is the sign of E cell if it's spontaneous in the forward direction? positive. Remember all those activities you guys did over the last week? That was kind of one of the big take-homes. Does this equation agree with that? We have a spontaneous reaction, negative on this side, right?
Yes. Negative.
Negative on that side times E cell. That negative is probably the most important part of this equation, and a lot of people leave it out. What's a negative? E cell? If E cell is negative, what does that tell you? The Gibbs free energy is positive. That means the reaction is only favored backwards from how they've written it. All right? Okay, so let's tie all this together. All right? You all right today, Mohammed? Yeah. All right. So I'm just going to go ahead and take this equation and plug in those guys over there. You guys following? Nope. Gibbs free energy at non-standard conditions. Right, this equation here. It's plugging in for delta G, delta G, delta G, plugging this in for it. Same thing for Gibbs free energy at standard conditions, right? We're substituting this. Standard conditions. So, you guys had asked how all these things fit together, so I'm glad Kayla asked and I can walk through this. Last part. Let's isolate E cell. How do you get this guy by itself on one side of the equation? Divide the whole right side by negative NF, right? What happens to this when you divide it by negative NF? Negative NF. This? Does it cancel out? No. All right. Welcome to the Nernst equation. You guys just figured it out. Okay. This equation allows us to say what is the E cell of a reaction. Remember all the stuff we were doing before was at standard conditions for the most part. If we can look up a value or calculate the standard potential of a cell, we can find the actual potential, and it's all basically the same equation as this. We're just using different terms for it. If we know what the actual concentrations are, then this allows us to convert between those.
No, it just makes you want to be smart forever.
So, do you guys want to know how this reaction actually works? Go ahead and calculate your Gibbs free energy at non-standard conditions for this reaction of glyceraldehyde 3-phosphate being converted to 1,3 by phosphoglycerol. What relationships are you guys going to use for this? Does this seem like a reasonable equation to use?
Yes.
So we want to know non-standard conditions. Do we know standard conditions? Yes. Can we figure out Q? Concentration of products over concentration of reactants?
We can, yes, sir.
You're right there, right? Micromolar. It's a micro sign, 10 to the negative 6. Does this look reasonable?
I can only do so much.
Where did this number come from?
37.
All right, so just a friendly reminder, we need to use Kelvin when we're doing any of these calculations. And then could you guys solve this?
Plug and play.
Plug and play, all right? So, going back to that first question, can this reaction drive the production of NADH and H+?
Because we have a temperature increase.
There wasn't a, well, okay, yes, there's a temperature increase, and Q is not 1. Right? So this being not 1 helped drive the reaction forward. And so we have enough energy to make this happen. You could also calculate E cell and figure stuff out here. I'm going to post all these slides after class. You can go and look through different ways to solve these types of problems. This is exactly what Activity 56 allows you to do with some of these questions on the final exam. It has been a fantastic semester. Thank you guys. I will see you on Monday for exam 3 or an office hour. Final is the same time as class. Oh, sorry. Yeah, it's 6 to 8 p.m. on Wednesday. You thought we thought it was what?
One that you thought